Okay, so these are the tension and Atwood machine notes and example problems. We'll start with tension. So the force of tension, which we label as T or F sub C, is the force exerted by a rope, chain, cable, and so forth. Basically anything that is not rigid that can pull something. And it's important to note that tension is a pulling force since you can't push with a rope. So tension can only pull on an object. Okay, tension can only pull on an object. Okay, so that's important to note. Now, how do we calculate the force of tension? Well, there's no specific formula that's like T equals this every time. But we can use Newton's second law to relate the motion of the object to the forces involved. So we can draw the forces exerted on the object in question. So in other words, we can draw a free body diagram. And we can write down Newton's second law, which on your AP formula chart is written in the format of A equals the sum of your forces divided by your mass for a direction in which the tension is directed. I would like to point out that your net force equation can also be written as F net equals MA. And you can also solve for tension using the same equation. So we'll do a couple of example problems. So example 1 says that we have a 0.25 kilogram container of animal crackers hangs at rest from 2 strings. So at rest is important. That means that it's not moving. And let's go ahead and jot down what our mass is. Our mass is equal to 0.25 kilograms. Okay, and it's secured from 2 strings to the ceiling and wall respectively. The diagonal rope under tension T2 is directed at an angle of 30 degrees from the horizontal. So this theta right here is 30 degrees. And it wants to know what are the tensions T1 and T2 in the 2 strings. So first thing we need to do is draw our free body diagram. So we will make our little dot for our object, draw our force pulling down, which is of course mg. We would have T2 pulling up at an angle. T1 is this force over here pulling to the left. Okay, and that's it on our free body diagram. We can add in, if we want, the angle here of 30 degrees. Okay, then we will decrease my line length, and then we need to do a pseudo free body diagram, since we have a force that's at an angle. So let's draw that. We have mg pulling down, T1 pulling to the left, T2 pulling up to the right, and then we're going to draw in the components of T2. So we'll have what we'll label as T2x. That's our x component. And then we'll have T2y. And then let's go ahead and see what those would be equal to. So T2x. Well, the angle that we're interested in is right here. So this is the 30 degrees. So that is right next to T2x. So that means that we're going to be using T2 times cosine of that angle. Then T2y will be equal to T2 times sine of the angle, because you can kind of slide this over and it should form a right triangle right there. All right, so now let's analyze our net forces. Let's start with our y direction. So F net y. Since it's at rest, it doesn't really matter which one you choose as up or down as being positive, but just for simplicity's sake, let's say up is positive. So we'll do T2y minus mg. So T2y minus mg, and since it's at rest, that's going to be equal to 0. So we can plug in that T2y is equal to T2 times sine of our angle. And that is still minus mg, and all of it is still equal to 0. Okay. Then we want to solve for T2. So we're going to first add our mg over. So we'll have T2 sine theta equals mg. Then we will divide both sides by sine theta. So we will wind up with T2 equals mg over sine theta. And now that we have that, we can just plug in our numbers. So we have 0.25 times 9.8, and then we divide that by sine of 30. When we work that out, when we put that in our calculator, make sure you have your calculator in degree mode for one, and then you should get that your T2 is equal to 4.9 newtons. Okay, so that's T2. So now we're going to look at our F net x to get our T1. So F net x, sorry, that's kind of messy, equals, and again, it doesn't matter which one is positive or negative, so let's do T2x minus T1, and since it's at rest, it will be equal to 0. So then we can substitute in that T2x is equal to T2 cosine theta, and I'm just going to do that here because I kind of am running out of space. So we have T2 cosine theta minus T1 is equal to 0. So then we can add our T1 over. So we have T2 cosine theta is equal to T1. So then we just plug our numbers in. So we have 4.9, that T2 that we just found, times cosine of 30. And that will give us our T1. So when we plug that in to our calculator, we should get 4.2 newtons. So that gives us T1. Okay, so now let's do another sample problem. Okay, example 2 says a 15-kilogram box sitting on a smooth table is connected to a free-hanging 5-kilogram mass by a stretchless matchless cord that passes over a small frictionless pulley. What is the acceleration of the two-block system in terms of g? So let's first say that m, like capital M, is 15 kilograms. Little m, we'll say, is the 5 kilogram mass. Okay, let's draw a picture for this. Might look a bit messy, and I apologize, but we have a table. We have a big M. We have a pulley. The cord is attached. Oh, my pulley bigger there. And then we have our little M hanging over the side. We have mg pulling down, tension pulling up on little m, and then we have tension pulling to the right on big M. Now, I'm not going to bother drawing my y forces for big M because it's not going to contribute to the acceleration of the box. So we can leave that alone. So I'm going to write my net force equation for my little m, because whenever this is released, it's going to accelerate down. So we'll say down is positive. So then we would have that mg minus tension is equal to little m times a. And we'll leave that for now, and we'll look at our equation for our big M. Well, the only force that's going to cause that block to accelerate, since it's on a smooth, aka frictionless table, is the tension. So we would have tension basically is our net force. So tension equals, tension equals big M times A. And then since this is equal to tension, we can go ahead and substitute that in over here. So we can have mg minus big M times A equals little m times A. And we want to solve this for A. So let's combine our like terms. So we have mg equals ma plus big M times A. And all I did was add this term right here over to the other side. And then you can factor out A. So we have little m plus big M. And that's equal to mg. So we can divide both sides by little m plus big M. And that will give us A is equal to mg over little m plus big M. And since it wants it in terms of g, that just means that we're not going to actually multiply it by this 9.8. We'll just keep it in g. So little m is 5 kilograms, right? And then we have 5 kilograms plus 15 kilograms on bottom, so that gives us 20. And then we have 5g over 20. So we can simplify that so that our acceleration comes out to be g over 4. And that gives us our acceleration in terms of g. And this should help you with your homework problems where I think it asks a question like that. So now, let's do one more tension sample problem. We have a rope of negligible mass supports a block that weighs 30 newtons. The breaking strength of the rope is 50 newtons. So what is the largest acceleration that can be given to the block by pulling up on it without the rope breaking? So that means that essentially that 50 newtons is like our maximum tension. So we'll set that as our tension, and that's equal to 50. So if we draw a free body diagram, we would have weight pulling down, and we would have tension pulling up. And since it's going to be pulling up, we would say that it up is positive. So when we do our F net Y, we would say tension minus mg is equal to ma. Now, we're going to need to know what the mass is. So over here to the side, remember your mass is your weight divided by your gravity. So that will just be 30 divided by 9.8. So your mass is going to be about 3 kilograms. So then we can use, now we can plug in and solve for acceleration. So we have 50 minus 30 is equal to 3 times our acceleration. So then 50 minus 30 is, of course, 20. Then we're going to divide by that 3 for our acceleration. So when we divide that out, we get 6.7 meters per second squared for our acceleration. Okay, so I hope that helps with your understanding of tension. So now we're going to go over Atwood machines. So Atwood machines are going to help you, so the objective of this section of the notes is to understand that tension is constant over a massless pulley, and we're going to solve problems for it, or we're going to actually set up how to solve problems for the Atwood machine. So an Atwood machine is an object where you have a pulley and then you have 2 objects over that pulley. Okay, and they're connected by a massless string, and it's an ideal massless pulley, meaning that the pulley doesn't require any mass to it. And the ideal pulleys are frictionless and massless, so they add no inertia to the system. The tension is constant in a light string passing over an ideal pulley. So your setup for Atwood machines is you always have to have a sign convention for positive and negative motion, and then you analyze each mass separately using Newton's second law. So let's see how that works. So this is showing that the motion is going counterclockwise. So that would mean that for M1, down is positive, and for M2, up is positive. Okay, so we will analyze each mass separately. So M1 is going to be labeled M1G for what's pulling it down, and then we have tension pulling up. Again, down is positive for that one. Then M2, okay, we have M2G pulling down, tension pulling up, and up is positive for M2. So let's do our F net Y for 2 first. Okay, so since up is positive, it will be tension minus M2G equals M2A. So if we solve this for tension, that becomes M2A plus M2G. And then we'll just hang on to that equation for now. We'll come back to it. Okay. Now we'll look at mass 1. We'll do our F net y for that one. This one will be M1G minus tension is equal to M1A. Then we can substitute in this here. Okay, so let's do that. So we have M1G minus, and then we're substituting in M2A plus M2G. Then that's equal to still M1A. Then we need to distribute this negative in. So we have M1G minus M2A minus M2G is equal to M1A. Now we need to combine our like terms. So I'm going to add M2A to the other side. So we have M1G minus M2G equals M1A plus M2A. And then we can factor out a G on the left side so that we have M1 minus M2. On the left side, we can factor out an A, so we have M1 plus M2. And then since we're looking for acceleration, we're going to divide both sides by M1 plus M2. So our acceleration will be G M1 minus M2 over M1 plus M2. Now this is your standard Atwood machine equation. So anytime you have an Atwood machine, if it's just two objects like this, you can just plug your masses in. Now let's see an alternative way to analyze this, because before we analyzed each mass separately. Well, you can also look at the system as a whole. Okay, so when you do that, okay, you still have your M2G pulling down, M1G pulling down. But since it's a whole system like that, tension is considered an internal force. So you don't actually apply it in your free body diagram. So since it's moving, again, counterclockwise, that means that this is our positive direction. Counterclockwise essentially is. So that means that we're going to have M1G minus M2G when we do our F net Y. We will have M1G minus M2G, and that will be equal to our total mass, so M1 plus M2 times the acceleration, because it's going to still accelerate at the same rate. And then you can again factor G out on this left side so that you have M1 minus M2. And then over here, you still have M1 plus M2, with A factored out, and then you divide both sides. And you wind up with, again, acceleration equals G times M1 minus M2 divided by M1 plus M2. So those are two different ways to analyze the same type of problem. I hope this helps you with your homework. So let me know in class if you have any questions, or you can message me if you have any questions. Hope this helps.